Hello everyone, my name is Oussama El Mhamdi from University Hassan First in Morocco, and I will give you a brief presentation of our work entitled Effect of Convection on Latent Heat Storage in a Tube and Shell Exchanger. For this, here is the plan. We have first an introduction, then problem configuration and models, after that results and discussion, and finally conclusion. Thermal energy storage systems have become a necessity to overcome the mismatch between energy supply and demand. Thermal energy storage can be used to store thermochemical, sensible, or latent heat, or a combination of these. Among the three forms, latent heat thermal energy storage has grown considerably in importance over recent years as a promising alternative to traditional systems. In this work, we will evaluate the effects on convection on the performance of a tube and shell exchanger. We have the problem configuration described in Figure 1. Heat transfer fluid HCF flows through the inner tube from the top to the bottom, and the outer tube is filled with a phase change material PCM. During the charging process, hot fluid at constant temperature circulates through the inner tube, while cold fluid at constant temperature circulates through the inner tube during the discharge process. Here we have the mathematical model. So we use the enthalpy model. We have a conservation of mass, conservation of momentum, and conservation of energy. After that, we have the numerical model, which is an axisymmetrical Lattice Boltzmann model. We have distribution functions, equilibrium distribution functions, and the source term. For resource and discussion, in this section, we will evaluate the effects of natural convection on latent heat storage. Figure 2 shows the evolution of the PCM liquid fraction for Rayleigh number equals 0 without natural convection, and Rayleigh number equals 2.5 times 10 to 5 with natural convection. The melting process in the system begins with the formation of a thin film of liquid around HCF tube. The layer increases in size until the time corresponding of the Fourier number FO equals 0.07. During this phase, the evolution of liquid fraction is the same in both cases, with and without natural convection. This is due to the fact that the fluid zone is thin with the dominance of the conductive regime. However, as the thickness of the liquid zone gains space, the effect of natural convection becomes significant, resulting in an intensification of heat transfer to the PCM and a greater amount of liquid fraction for the case with natural convection. Also, the effect of natural convection can be illustrated by the behavior of the temperature at the outlet of the channel in Figure 3. Indeed, for Rayleigh number equals 2.5 times 10 to 5, the thermal transfer of the fluid to the exchanger is greater, which causes a thermal gradient between the inlet and the outlet of the channel. In order to understand the transfer mechanism involved during the phase change process, we have drawn isothermal lines and streamlines for different instants as shown in Figure 5. For Rayleigh number equals 0, the isotherms remain parallel to the wall during the melting process. The transfer mechanism is thermal conduction, which takes place mainly in the radial direction. Initially, the melting front progresses rapidly and the heat flow transmitted is then significant. As the interface progresses, the thermal resistance between the hot zone on the HCF side and the cold zone becomes important, and the Nusselt number decreases with slower progression of the interface. For the case of Rayleigh number equals 2.5 times 10 to 5, the isotherms are almost parallel to the wall at the beginning of melting due to the dominance of conduction. As the melting front progresses, the fluid zone becomes larger and larger, which promotes the appearance of flow cells in fluid zone. This causes curvature in the upper side of the interface. On the other hand, the flow cell accelerates the heat transfer to the solid zone, which results in the rapid melting of upper part of the PCM. To conclude this work, we can say that the convection accelerates the melting process and thus reduces the melting time. Thank you for your attention.